Hey everyone. In the last video, we reviewed the delta-epsilon definition of a limit, which I've rewritten here for us to look at. In this video, I would like to write a couple of proofs that limits exist by using this delta-epsilon definition. So let's first review. I want to point out a couple of things before we actually write the proofs here. But we said that the limit, as I'm going to work backwards here because we've already worked this out in the last video, but we said, though, that the limit as x approaches a, whoops, make this a different color. So the limit as x approaches a of f of x, the colors are not changing, so of f of x is equal to L, provided we can find, so provided that for every epsilon greater than 0, we can find a number, which in this case we call delta, which depends on epsilon, such that when x minus a, so notice this right here corresponds to this, is less than delta, then f of x minus L. So f of x here minus L has to be less than epsilon. So I've color-coded this so that we can see all the parts, right? But x minus a, this part comes from the boundary of the limit down below. It has to be less than delta, so we make this we have to find the delta for which this formula is satisfied here, right? Or this statement is satisfied. Then f of x minus L should be less than epsilon. All right, and so we can see that f of x minus L looks kind of like f of x equals L. The arrow and the equal sign kind of become minus signs in what we have to actually use here to write our proof. So this is just kind of a review of the definition. Let's actually write the proof now. So here's our first example. We want to prove that the limit as x approaches 5 of 3x minus 4 is equal to 11. Well, anytime we write a mathematical proof, we want to be kind to the reader. This is a phrase that I use. And what I mean by that is we want to be very clear about what we're proving, when the proof begins, when the proof ends, and in between we want to be very clear about what steps we've taken and why they are true. So we always start our proofs by saying that we're writing a proof. So we write proof, right? And then we are going to very carefully work through this limit definition to make sure that the definition holds for this statement that we have here. Okay, so remember that the first part of the definition says that whatever we do has to be true for every epsilon greater than 0. So the first step of our proof is going to be to fix this number epsilon greater than 0. All right, and then we need to determine the delta for which this is true. And the delta is going to depend on epsilon. It's going to be different for every choice of epsilon. So at this point, we write put delta equal to blank. We don't know what delta is going to be yet, right? It's going to be part of the proof, is determining what delta should be. And this statement then, it needs to be filled in, right? But we're always going to write put or set delta equal to blank, and we're going to have to fill this in, all right? Now, we need to write out the rest of the definition, right? Remember in our definition that we are supposed to assume, or say like if, right, x minus a is less than delta and greater than 0, then we have to show that this will be true for our epsilon, right? And that's where we're going to determine our delta. So that's the next step. We just rewrite the definition and we plug in the values that we actually have for our limit. So if x minus a is less than delta. So x minus a in our case is x minus 5 for this limit, right? This limit, we have x minus 5. And this should be less than delta. Then what's got to be true? Well, remember we had our f of x minus L should be less than epsilon. Well, we can't just say that it's less than epsilon. We have to work it out, right? We have to use our assumption. So in this case, our f of x minus L is going to be 3x minus 4. That's the f of x, right? 3x minus 4 minus L. L is 11 for this example. So minus 11. We want to be able to write this down. We want to be able to deduce that this must be less than epsilon given our assumption that x minus 5 is less than delta. So we can just do some algebra now. We can combine with these absolute value bars have to stay here, right? We can just combine these two. So this can be written as 3x minus 15. And then we notice that there's a common factor of 3, which can be factored out. 3 is a positive number, so it can come straight out of the whole thing. And this can be written as 3 times what's left, x minus 5. And at this point, we notice that this term right here, this x minus 5 that we have, is exactly what we have made our assumption about in the previous line, right, in the if portion of our proof. So therefore, we've assumed that this is less than, the 3 has to hang around, but it's less than 3 times delta, right, because this delta, this x minus 5 was assumed to be less than delta. Now we want to try to get this to equal epsilon. Go back to our definition. We've got making our assumption that x minus a is less than delta should lead to this difference, f of x minus l, being less than epsilon. So we need to get an epsilon in here. How are we going to do that? Well, now is when we make our choice of delta, right? So we now set our delta to be equal to, what's it going to be? We want this to just be epsilon, so we have to divide through, right? So we need our delta to be equal to epsilon over 3. And let's see what happens now. So now we have that this is equal to 3 times epsilon over 3 by this, right? By using this value that we've just set this to be, and of course those cancel, and this is equal to epsilon. All right, so now we've got if x minus 5 is greater than 0 but less than delta, then our function 3x minus 4 minus our limit 11 is less than epsilon. This symbol right here rules. This less than symbol rules. All right, and we have to now state our conclusion of this proof. So by the delta epsilon definition of limit, we have shown, right, that the limit as x approaches 5 of 3x minus 4 is equal to 11. That's the end of the proof. We put this little box, and I always like to add a smiling face. So there's a proof, a delta epsilon proof that the limit exists. You don't need to color code your proofs, but you have to write all this information. All this needs to be here. Every single thing here needs to be here. All right, let's do one more. So this next one is going to be a quadratic function, x squared minus 4. That's the minus 4x. That's the function. We want to take the limit as x approaches 3, and that should equal negative 3. All right, so for this one, we need to do a little bit of preparation, because the fact that this is a quadratic function is going to change things a little bit. So before we write the proof, we're going to do some prep work here, preparation. First of all, we know that we're going to assume, just based on our last proof, we are going to assume that x minus 3 is greater than 0 but less than delta, right? And we want to know, how does that x minus 3 factor in to this function here? And factor in, it was a choice, purposeful choice of words, because look what we're going to have to do here. We're going to have to compute, right, x squared minus 4x minus negative 3 as part of our computation, and arrange this and then factor it, actually factor it. So this becomes x squared minus 4x plus 3, and this of course factors to be x minus 1 and x minus 3. So x minus 1 times x minus 3, and absolute values can distribute over this, so this just becomes x minus 1 absolute value times x minus 3 absolute value. Now, why are we doing the prep work? Why didn't we just write the proof, right? Well, look what we have. We have x minus 3 is less than delta. That part is taken care of, right? So we're happy about that. But the question becomes, what are we going to do with this x minus 1 term, right? So in other words, how is x minus 1 related to this x minus 3? So what we do then is we just kind of make an arbitrary choice. So let's say, suppose that our x minus 3 is less than 1. So this distance is less than 1. Why 1? Because it's a nice number to work with, right? You can actually choose any number you want here at this point. So, but suppose x minus 3 is less than 1. All right, then what happens to x minus 1? Well, x minus 1 absolute value is the same as, I'm going to write this kind of in a funny way, but I want to get an x minus 3 involved in here, right? So it's going to be equal to x minus 3 plus 2. Negative 3 plus 2 is just negative 1. So I haven't changed anything. I've just changed the way that it looks, right? And now at this point, what can I do? Well, there's something called a triangle inequality. And if I wanted to break this up, this absolute value up at this point, I can do it, but I get a different symbol here, right? So what I end up with is that this is less than or equal to x minus 3 absolute value plus the absolute value of 2. This is by something called the triangle inequality. So if you don't remember this, please look it up. So triangle inequality. It basically just says that the length of one side of a triangle is always less than or equal to the sums of the lengths of the other two sides. All right, and this is, of course, then, based on our argument here, this is less than 1 plus 2, or 3. All right, so what we know then is that if x minus 3 is less than 1, then we can bound x minus 1, right? X minus 1 is then less than 3. And we get an actual number here. So now we're ready to write our proof. All right, and because we chose this number 1 here, this number 1 is going to show up in our proof again. So that number 1 we're going to see again. So let's do it. All right, we've done our prep work. Now it's going to look like we just kind of made a we just knew a lot about what was going to happen, right? So let's write our proof. Again, we always start with fix epsilon greater than 0 and put delta equal to, this time we're going to set delta equal to the minimum of 1, it's supposed to be a 1, of 1 and blank. So we still need to determine the blank, right? That's going to come from our calculation. We're almost there. It won't take much work because we don't have to redo everything that we just did up above, right? But it's going to be the minimum of 1 and blank, and the 1 is the number that we chose here. If you choose a different number, that's what has to go in this minimum here. And then we say if our our x minus, remember our limit is as x approaches 3, right? So if x minus 3 is less than delta, but greater than 0, then we can compute, remember our difference was then, I'll write it out, f of x minus L, right? Which in this case was equal to x squared minus 4x minus negative 3. We've already done the work to factor this, right? This factors to become x minus 1 times x minus 3. And we now know that we want this to be less than the difference, less than delta on one hand, right? So it's less than delta on one hand. But it's also this portion right here, the x minus 1, by our work from up above, is going to be when x minus 3 is less than 1, this is less than 3, right? That's the work that we have here. So from this portion right here, we can write then that this is less than 3 times delta. So the 3 comes from our work up above. That's the reason that we have this 1 here. And the delta comes from this portion right here. And this statement right here now tells us how to choose the other portion of our minimum, right? So it's just a coincidence that we got a 3 in both cases, but again, we want this to be delta to be the minimum of now 1, because we want this inequality, and epsilon over 3 because we want this next inequality. All right, so by the way, whichever one's smaller, the minimum is always smaller than each of the entries, right? So less than or equal to each of the entries. So this means that delta's, if 1 is the maximum, then epsilon over 3 is smaller. So the next thing we're going to write is not going to be a problem. Or in the other case, right, 1 is smaller, and then this inequality is no problem. So at this point, we have to write that this is now less than or equal to, instead of equal to. We just had an equal to in the last one, but now it has to be less than or equal to 3 times epsilon over 3. And this is, of course, epsilon. All right, so this one's a little more complicated. The complication comes in the prep work, but the writing of the proof, these lines, these just look like you knew what you were doing, because you're probably not going to box everything out the way I did here either. But we still have to write our conclusion, right? So by the delta epsilon definition, it's really the only definition, but it's good to remind yourself, delta epsilon definition of limit, we have shown then that the limit as x approaches 3 of x squared minus 4x is indeed equal to negative 3. This box tells us we're done with the proof, and we smile because we're happy.